A warm good morning to one and all present here. I'm honored to extend a warm welcome to each and every one of you to this insightful seminar presentation on the topic Low Power Wide Area Network Technology. My name is Fiskaros Thomas and my guide is Professor Rinsi Merimworki. Here, we will explore and engage with the topic that holds great significance in any field. To guide you through this agenda, I have structured the presentation into introduction part, history, steering technologies, architecture of LPWAN, wireless technologies for M2M communications, why do LPWANs matter to IoT, wireless access for IoT applications, mixed IoT architectures, LPWAN technologies, classification, wireless technologies, characteristics, need of LPWAN, design objectives, advantages and disadvantages, applications, challenges, recent developments, future works, conclusion, and references. So, coming to the introduction part, LPWAN, as the name suggests, offers a unique blend of low power consumption and an expansive range, making it a key enabler for a multitude of applications in diverse sectors. It is a wireless wide area network technology that interconnects low bandwidth, battery powered devices with low bit rates over long ranges. So, there are a few examples that are smart metering, infrastructure monitoring, and security monitoring. So, coming to the smart metering, it involves using advanced sensors and communication technology to measure utility consumption such as electricity, gas, or water. These meters provide real-time data, enable more accurate billing. So coming to the infrastructure monitoring, it employs various sensors and IoT devices, monitor the condition and performance of buildings, roads, bridges, and so on. This data helps detect maintenance needs and safety. And coming to the security monitoring, it has utilizing cameras, sensors, and technologies. And so, let's move on to a history part. It says, during the time of 2000s and 2010, a number of groups and consortiums, including the Industrial Internet Consortium and the Internet of Things Consortium, attempted to standardize IoT technology and protocols. With the establishment of the IEEE 802.154G standard in 2009, the foundation for low data rate wireless communication was set, making it ideal for outdoor and smart grid applications. Global IoT Network was created by the 2010 founded Sigfox company employing ultra narrowband technology. And by the time of 2011 to 2012, wearable technologies and smart home appliances gained popularity as Internet of Things use grew. The Nest Learning Thermostat, a well-known smart home appliance, was introduced by Nest Labs. LoRa was introduced by Semtech in 2012 and quickly gained popularity for use in many IoT applications thanks to its unlicensed spectrum usage, extended range, and low power consumption. However, the establishment of the LoRa Alliance, a joint venture of industry titans, in 2015 marked a crucial turning point. And by the time of 2013 to 2019, the cellular industry understood the necessity to integrate LPWAN capabilities into current cellular infrastructure in order to continue the path of LPWAN improvements. As a result, the third generation partnership project, it can be shortened as 3GPP, standardized narrowband Internet of Things, or NB-IoT, in 2016. And by the time of 2020 to 22, the General Data Protection Regulation went into effect. And major tech companies like Amazon, Apple, and Google started to compete in the smart speaker market, bringing voice assistants to more homes with devices like Amazon Echo and Google Homes. And also in the time of 2019, IoT continued to grow in healthcare thanks to the COVID-19 pandemic. which accelerated its adoption in the field and highlighted the value of remote monitoring and work. Low-power wide area network technologies will continue to develop and gain acceptance in 2020, especially in the context of the developing Internet of Things market. The development of LPWAN systems over time has led to a wide range of IoT applications, including smart cities, agriculture, industrial automation, and asset tracking, which have paved the way for a connected and productive future. So these are about the history part, and let's move on to the technologies. So in the technology part, it contains 4 steering technologies, that is Sigfox, LoRaWAN, NB-IoT, LTE-M. So coming to LoRaWAN, it operates on LoRa modulation technique. Semtech developed LoRa as one of the primary technologies in LPWAN, which enables long range, low power and reduced data rate. It uses the series modulation technique, that is crisp signal spectrum. It is a type of spread spectrum modulation that employs crisp signals for transmitting and receiving data. So, what's crisp signal? It's a signal in which frequency continuously increases or decreases with time. Maximum coverage area up to 5 km in urban areas and about 20 km in rural areas. So about spread spectrum, it's a method of transmitting radio signals by spreading the signal over a wide frequency band. Now coming to the next one, that's the Sigfox. It is an unlicensed, low power and inexpensive wireless network based on ISM standard. Initial Sigfox only supported communication from end nodes to base station or the uplink using BPSK modulation. So the BPSK modulation utilizes 1 Hz to transmit 1 bps, and hence Sigfox uses 100 Hz frequency to broadcast 100 bps. It has a coverage of 10 km in urban areas and 40 km in rural areas. And coming to the NB-IoT and LTE-M, NB-IoT is optimized for low power, wide area IoT applications with small data transmissions. So coming to LTE, it is designed for high speed, low latency communication, often used in smartphones and data center devices for fast internet access. So these are about LoRaWAN, Sigfox, NB-IoT. And coming to the architecture of LPWAN, this is a figure of architecture of LPWAN. So coming to the explanation, end devices, or it can be also called as IoT devices. Those are sensors, devices or objects that gather data and transmit it to LPWAN networks. These gadgets frequently have minimal power. LPWAN devices' primary job is to gather data and react to inputs from LPWAN. The access station and the IoT networks receive collected data over a specified radio channel. The radio link for device administration and device traffic exchange is provided by access station. The data collected are given to gateway, which is interfaced with the access station. Network server controls the communication between applications and endpoints. Data received from gateways verifies and decrypts it. So these are about that part. And coming to the application server, it says it processes the data according to demands of IoT application. So these are the explanation about the architecture of LPWAN. And so coming to the wireless technologies for M2M communications, the wireless technologies are of 2 types, mainly that are short range M2M wireless technologies, and then long range M2M wireless technologies. So coming to the first part, that is the short range M2M wireless technologies. There are a few numbers that are of short range, that are Bluetooth, Zigbee, Wi-Fi, and so on. So coming to Zigbee, is a wireless communication standard used for home automation and IoT devices. It operates on low power, low data rate, and short range transmission. It is suitable for connecting devices with home or small areas. So that's about Zigbee. And coming to Bluetooth, is a wireless technology used for short range communication between devices. data and information along short distances within 10 meters to connect phones, headphones, and speakers. And coming to the next one, that's Wi-Fi. Wi-Fi IEEE 802.11, also called Wi-Fi, is another short-range technology that enables communication between wireless devices within a limited distance. It is also commonly used for closed environments such as homes and offices. It uses 5 GHz and 2.4 GHz in the ISM bands. So the other part is the long-range M2M wireless technologies and contains LoRaWAN, Sigfox, and Sigfox as we have discussed before. Coming to LoRaWAN, LoRa stands for Long Range, a physical layer technology for long range, low power wireless communication system invented by Semtech. LoRa can cover more than 15 km on the ground and close to 30 km on the water using the 868 MHz ISM band with a transmit power of 14 dBm and the maximum spreading factor. So coming to Sigfox. Sigfox is another proprietary LPWAN solution that operates in the 200 kHz band of the publicly available spectrum to transfer 100 Hz wide messages at a data rate of 100 bps or 600 bps. The last part is random phase multiple access. The proprietary LPWAN technology, known as RPMA, was proposed by IGNIO, formerly known RAM. Unlike LoRa and Sigfox, RPMA does not use subbands. It instead uses the global 2.4 GHz ISM band to realize a worldwide vision of the LPWAN. The two parts are Telensa and NB-IoT. So Telensa uses UNP, a patent-ready technology, to realize end-to-end communications for IoT applications. It operates in the licensed X radio spectrum, including ISM bands around the world. So about NB-IoT, as we have discussed before, is a new LPWAN solution called NB-IoT, which uses mobile network providers. It was designed and standardized by 3GPP. NB-IoT relies on a decreased data rate no higher than 158.5 kbps on the UL and 106 kbps on the REL to reduce device cost and battery consumption. So these are about the wireless technologies for end-to-end communication. And so coming to the next part, that's why do LPWAN matter to IoT? So that's the question. And IoT devices so we can say that IoT refers to devices, objects and systems that communicate with each other through internet. So LPWAN are pivotal to the flourishing landscape of IoT. At the core of their significance lies the ability to facilitate seamless communication between IoT devices with minimal power consumption. IoT devices function for a long period of time without the need of frequent battery replacement because of LPWAN's low power consumption. And it also has extensive communication range, cost-effective scalability, and so on. LPWAN is a sensible option for implementing IoT networks at scale and supporting the growth of connected devices because to its affordability and scalability. So these are the reasons why do LPWANs matter to IoT. So coming to the next part is the wireless access for IoT applications. So wireless access networks for IoT applications span different geographic ranges. As shown in the figure will be discussed in the next slide. So before that, let me explain the parts that are the 4 parts that are wireless personal area networks, wireless local area networks, wireless neighborhood area networks, and the wireless wide area networks. So coming to wireless personal area networks, that is WPANS. It's based on RFID and NFC. These are short-range networks designed for communication between devices in close proximity. RFID and NFC technologies are commonly used for quick, secure, and short-distance data exchange. So coming to the next one, that's the wireless local area networks, or the WLANs. So it is designed for high-speed data exchange. WLANs are intended for high-speed data exchange between devices over a campus-wide area, typically limited to a few hundred meters. Various flavors of the IEEE 802.11 standard, such as Wi-Fi, fall under this category. So coming to the next one, that's the wireless neighborhood area network, or the WNAN. It's a new architecture system focused on broadband wireless local distribution. It has with the application service areas more than a metropolitan area, but larger in a local area network. So the last one, that is wireless wide area networks, or the WWANs. It's for catering to large areas. WWANs are designed to cover larger geographic areas compared to WLANs and WNANs. They provide wireless connectivity over extended distances. In summary, each type of wireless networks serves specific purposes based on the range and coverage required. WPN is for close proximity, WLAN is for high-speed data exchange within a limited area, WNAN is for broadband distribution in a medium-sized service area, and the WWAN is for broader coverage over larger geographic regions. So in the slide we could understand the range, the short range, that's about 10 to 100 meter, then the short to medium range, that's about 100 to 100,000 meter, then medium range, that's about 10 kilometers, and the long range, that is about 100 kilometers, and so on. So this is the wireless access geographic coverage. And coming to the next slide, that's about the mixed IoT architecture. It's about the Internet of Things. So it has four main basic parts, that are IoT endpoints, base station, network server, and IoT SaaS. Or it's also called software as a service. So by using many communications to collect data. So coming to IoT endpoints, they collect and transmit data are collected and transmitted by devices or sensors placed at different locations, and the networks used for transmitting are Sigfox, LoRa, and LoRaWAN technology. And then it is about IoT endpoints. And the next part, that's the base station. There is no data processing or collection in this part, but to enable communication, data are collected and is passed to IP protocols. So the next part, is the network server. Speed and bandwidth of transmitted data can be adjusted by giving a request. The two network servers are LoRaWAN base station and Sigfox base station, as we can see in the figure. And coming to the last part, that's the IoT SaaS. By storing the data received from IoT devices to a cloud platform, and then visualization, processing, and integration part. So this is about mixed IoT architecture, and so we could understand from the figure. And this is explanation regarding the mixed IoT architecture that we have discussed now. So coming to the next part, that's the topologies. The two main topologies are the star topology and the mesh topology. That are the two prominent topologies that are preferred in the majority of network implementations. So coming to the star topology part, star topologies. All devices are connected to a central hub or switch. It relies on central hub. If the hub fails, the entire network can be affected. In star topology, it can be less scalable, as adding more devices may require upgrading the center hub. If the center hub fails, the entire network may be compromised. However, individual device failures don't impact others. Easy to install and maintain compared to mesh troubleshooting is simplified. All data traffic passes through the central hub, which may lead to congestion. These are about the star topology, and coming to mesh topology. It's a topology. We can understand that each device is connected to every other devices in the network. So we can understand that from this figure 10. And It offers high redundancy. Multiple paths exist for data transmission. So if one link fails, the alternative paths are available. It's more scalable. Additional devices can be easily added without disrupting the existing network. And then more complex to install and manage due to the multitude of connections, offers decentralized control. And data can take multiple paths, reducing congestions, and many more points. Like data can take and improving overall network performance through mesh technology. And coming to summary part, we could know that from coming to summary, SAT topology is simpler, easier to manage, but has a single point of failure. Mesh topology offers redundancy, scalability, and reliability, but can be more complex to set up and maintain. The choice between them depends on the specific requirements and properties of the network, priorities of the network. And these are the classifications regarding the LPWAN technologies. The two main classifications are 3GPP, licensed band and unlicensed band. So licensed band is also called 3GPP, that we'll be discussing in the coming slides, and the other one is non-3GPP, that's unlicensed band. So it's 3GPP is classified in three types, that are LTM, NB-IoT, EC-GSM, and then the 3GP parts that are weightless, and the other full site that are Sigfox, LoRaWAN, RPMA, Chalensa, D7AP, IEEE 802, NBFI. And coming to weightless, it contains weightless W, weightless N, weightless P, and others. So these are about the classification part. And coming to the next slide, it contains wireless technologies. So as we have said before, there are different LPWAN wireless technologies which are separated into two groups based on the frequency bands they use. Those are licensed frequency band and the unlicensed frequency band. And there is one more part, that's the weightless. So coming to the licensed frequency band. Licensed frequency band, it has a range of radio frequencies over which regulatory authorities grant licenses to specific entities, ensuring controlled and organized use of the electromagnetic spectrum. It's the most prominent and widely used wireless technology, and there are few authorities that are governing them, that grants the licenses. And coming to the unlicensed LPWAN technologies, from the name we could understand those are unlicensed, that they have no any authorities, and it's a range of radio frequencies that can be used without the need for a specific license from regulatory authorities. Devices operating in unlicensed bands must adhere to certain technical standards to avoid interference with other devices sharing the same spectrum. So coming to the weightless, it's an open LPWAN technology operated in sub-gigahertz frequency bands and managed by weightless special interest groups, also called weightless SIG. This technology consists of three types of standards, including weightless W, which operates on licensed bands, and weightless N and weightless P, that both operates on unlicensed bands. So coming to the characteristics, there are various types of characteristics. The first one is long range connectivity. It's one of a factor. In contrast to traditional short range wireless sensor networks, the design goal of LPWANs is to offer wide range coverage at low power and low cost. We have discussed these points in the above slides, and coming to the other one, that's the low power IoT devices are expected to operate for a very long time without the need to replace the battery. The other one is low deployment and operational cost. A major factor contributed to the rise of LPWANs is its low cost. LPWAN's cost effectiveness stems from its ability to balance low power consumption, long range coverage, and simplify infrastructure. The other one is reliability and robustness. It's also critical aspects of LPWAN technologies to ensure consistent and dependable communication for IoT devices. The other one is potential to scale. Avoidance of multi-hop topology gives high potential to scale the LPWANs. So, coming to the next part is the need of LPWAN. So, what is the need of LPWAN? The imperative for Low power wide area network arises from the inherent shortcomings of conventional connectivity options like cellular networks and Wi-Fi, as these often prove unsuitable for a significant array of Internet of Things applications due to limitations in range, power, efficiency, and affordability. LPWAN serves as a pivotal solution by providing an effective and economical alternative that extends connectivity over vast distances, addresses power consumption concerns crucial for IoT devices situated in remote or other challenging environments where frequent battery replacement is impartial, and consequently it emerges as an indispensable technology, fostering widespread integration and enabling innovative applications across the device industries, ultimately contributing to the realization of a more interconnected and streamlined world. So it's about the need of LPWAN. And coming to the next part is the design objectives. So there are a few design objectives. The first one consists of wide coverage. One of the key features of LPWAN is its capacity to transfer data for individual devices across large distances, resulting in LPWAN's long-range transmission capabilities. The other one is low cost that we have discussed in many slides. The commercial success of LPWANs is dependent on the ability to link a number of end devices by using inexpensive hardware and providing connectivity at a lower subscription. The other one is ultra low power operations. LPWAN technology supports this requirement by enabling low power operations over IoT devices. The other one is scalability. One of the major design objectives of the LPWANs is scalability. When an increase in the number of devices connecting to the existing network will not distribute the network performance. So the other one is interference management. In LPWAN technology, it involves strategies to mitigate signal disruption caused by external sources or overlapping networks. Quality of service LPWAN. Technologies are targeting a diverse set of applications with varying requirements. So the other one is low power consumption. Thus, the LPWAN aims to minimize energy usage, allowing devices to operate on small batteries for extended periods, sometimes up to several years. So the other one is a low data rates. LPWAN prioritize transmitting small amounts of data at a time, making it suitable for applications that don't require high-speed data transmissions. The other one is adaptability to various use cases. So these design goals and objectives are collectively enable LPWAN technologies to cater to a broad spectrum of IoT applications that require long-range, low-power consumptions with relatively low data rates. So the next part is the advantages and disadvantages part. So the advantages are it has fast deployment, diverse application, interoperability, high penetration and coverage, long range, and low cost, and many more. And coming to the disadvantages part, it has latency, limited bandwidth, security concerns, coverage challenges, dependency on network operators, and the initial set of complexity and many more. So coming to the application part, there are many applications in the LPWAN technology. The first one is the logistics. It's by facilitating effective asset tracking and monitoring, streamlining supply chain operations, and enhancing overall logistics management. LPWAN plays a significant role in logistics. In the logistics sector, LPWAN is the best technology for tracking shipments, keeping track of inventory levels, and controlling fleet operations since it offers extensive coverage, low power consumption, and affordable deployment. Smart buildings. Smart buildings are the one. It's by utilizing the advantage of long-range, low-power connectivity. LPWAN in smart buildings aids in the creation of environmentally friendly, productive, and economically viable environments. So the figures are shown inside, and we could have a small understanding by seeing the figures. And coming to the next one is the smart agriculture. The agriculture overlaps with some of the other domains discussed in this study. Agriculture applications include animal tracking, environmental monitoring, and infrastructure control. The other one is military and defense. LP1 technology offers a versatile and valuable solution for various military and defense applications, enhancing communication, monitoring, and operational efficiency while minimizing power consumption. The last one is healthcare. The LP1 provides a smooth balance between security and affordability with improved system energy efficiency for healthcare applications. So that was about the application part and advantages, disadvantages, and so on. So let me move on to the challenges part. It contains these parts that are scalability, further performance studies, catering to future needs, standardization, security, and so on. Challenges are involved in many parts that are. First one is the scalability. Scalability is one of the main challenges. That is, increasing structure of horizontal scalability allows more devices to connect to each base station, and more base stations to be deployed throughout the network. It's one of a challenge. The other one is a further performance study that the more studies are coming up and has been rapidly evolving, and further performance studies have been conducted to enhance its capabilities. So the other one is catering to future needs. If LP1s cannot meet increased expectations, this could lead to potential disenhancement and negatively impact the acceptance of LP1 technology. So the other one is standardization. So developing a method for devices to easily communicate with those utilizing different standards provides an ongoing challenge with significant potential rewards. The last one is the security. It's involved in many cases. So without adequate security, LP1s will not be commercially viable. So these are about the challenges part. And coming to the recent developments, we could know that in addressing the diverse connectivity needs of IoT deployments, solutions have been explored to create hybrid systems that combine low power wide internet technology with other wireless technologies like Wi-Fi or satellite communications, providing a comprehensive range of connectivity options. So, LP1 has demonstrated its adaptability and promise across various fields such as agriculture, environmental monitoring, asset tracking, smart cities, and healthcare. Notably, LP1's recent applications in smart cities, smart agriculture, smart healthcare, and environmental monitoring showcase its versatility and relevance in different sectors. Moreover, efforts by LP1 service providers to expand network coverage contribute to making these technologies more accessible and beneficial for a wide array of use cases. Recognizing concerns about the security of IoT devices, advancements in security protocols, and features for LP1 have been introduced. So, these are the recent developments we could understand, and recognizing concerns about the security of IoT devices, the advancements in security protocols and features for LP1 have been introduced, ensuring the secure transfer of data and addressing vulnerabilities across with IoT deployments. So those were the recent developments, and there are also future works, and those include architecture designing for core level integration, unified data management, enhanced efficiency, security enhancement, IoT, edge computing used in disaster response. So coming to unified data management, we can know that this involves designing a system where data is organized and managed in a cohesive manner, allowing for seamless access and utilization across various components. It ensures a standardized approach to handling data, making it easier to retrieve, update, and analyze. So the other one is enhanced efficiency. So in the context of architecture designing, this would focus on optimizing process and workflows to improve overall system performances. This might include streamlining communication between different modules, optimizing algorithms, or implementing parallel processing to handle tasks more efficiently. Those were about the enhanced efficiency, and coming to them. Security enhancement, architecture should incorporate robust security measures to safeguard against unauthorized access, data breaches, and other potential threats. This could involve encryption protocols, secure authentication mechanisms, and regular security audits to identify and address vulnerabilities. So another one is IoT edge computing. So we can add this refers to designing architecture that can efficiently handle the processing and of analysis of data at the edge of the network where IoT devices are located. This approach reduces latency, bandwidth usage, and dependence on centralized cloud resources by processing data closer to its source. So the last one is using disaster response. That is, designing the architecture with disaster response in mind would involve creating a system that is resilient, scalable, and capable of handling emergency situations. So these were about the explanation about future works, and coming to the conclusion part, we can know that as the deployment of Internet of Things applications is set to increase significantly, there is a growing demand for network technologies that are not only efficient but also offer low power and long range capabilities. The use cases discussed in this paper aim to guide readers in evaluating the available solutions, helping them determine which technology aligns best with their specific requirements. This in turn enables them to make well-informed decisions and strike compromises when necessary. Furthermore, the paper outlines both opportunities and challenges associated with the future use of low-power wide area networks in IoT applications, offering insights and directions for future research in this rapidly evolving field. So, these are the references. Thank you all.